Okay, we'll get started. In this section, we're going to be talking about 8D and 8E. So 8D is wave interactions, and 8E is a particular type of wave, which would be sound. So waves, again, 8D, we'll get started with. Waves can interact with each other, and they can kind of do different things when they interact. So the first type of interaction would be if they line up with each other, if the crests and troughs of a wave line up with each other, their amplitudes are going to add. And that's called constructive interference. So this is an example right here. So you can see the red and the blue waves, the crests line up, their troughs line up. If that happens, what's going to happen is their amplitudes are going to increase. They're going to add to one another. So if this amplitude was like 1 meter, this amplitude was like 1 meter, this crest. If they line up with each other, you're going to create a new wave. It's going to result in this new wave, and this amplitude is going to be 2 meters, and this amplitude right here is going to be 2 meters. So again, it's going to basically add. It's going to create a wave that's bigger than either one. So that's constructive interference. That's if the waves line up with each other. The other thing that can happen is you could have destructive interference. And that's, you might have guessed, if the crest and troughs of the wave do not line up with each other. Their amplitudes are going to cancel instead. So like if you had this over here, you see the blue and the red. A crest of the blue lines up with a trough of the red. Trough of the blue lines up with the crest of the red. They're kind of out of sync with each other. So let's just say they each had an amplitude of 1 meter. So what's going to happen when they combine? They're going to basically cancel each other out, and you're going to get this zero line. So again, when they don't line up with each other, they're going to detract from one another for the resulting wave. It doesn't necessarily have to be zero. This was zero because they did the perfectly same amplitude, but they might have, if this one was 2 meters, this one was 1 meters, you'd get a smaller wave. So again, if they don't line up with each other, they're going to cancel out, may or may not cancel to like an absolute zero wave, like this. So that's wave interaction. So there's two ways really. We're going to look at how they interact with each other. Move on to the next section, which would be 8E. 8E. Here we go. So 8E is talking about a specific type of wave, and that's going to be sound. So sound is going to have a couple of properties that we're going to be looking at more specifically. So it's important to remember that sound is a mechanical wave. Mechanical meaning that it needs something to travel through, and longitudinal. So longitudinal meaning that the energy travels parallel to the direction of motion. So for example, if you were to look at a sound wave, the air molecules would look like this. There'd be places where they're bunched up, places where they're less bunched up, places where they're really bunched up, places where they're less bunched up, right? You'd have that kind of repeated thing. You'd have compressions, compression, compression, compression. Then you have rarefactions in the middle where it's less dense, and the energy would be moving this way. So again, it's a longitudinal wave, sound. And sound waves are going to be produced by the vibration of objects. So that's really what creates sound. So we're going to be looking at a couple different properties of sound. The first is pitch. So pitch is the highness or lowness of a sound, and pitch is related to frequency. So let's look over here. This would be a lower frequency sound. See, this isn't even one full cycle here. So this would be again, low frequency, low pitch, basically. So this might be like bass in a song, bass drum, sure. And then if we move over here, this was what a higher pitch would look like, right? It's a lot, the frequency is a lot higher pitch. So again, this might be like a human voice. This might be like bells or something, high pitched, high frequency, high pitched. The other property is loudness. And loudness of a sound is directly proportional to amplitude, meaning if the amplitude goes up, that must mean the loudness goes up. So we'll look over here. So a quieter sound would be like the human voice. Typically, if you're just talking, or let's say talking. So if you're just talking, that's relatively quiet. You can have a pretty low amplitude, but again, if you stand near a jet engine, that's a lot louder of a sound. You're gonna have something that looks more like this over here with a higher amplitude. So again, amplitude is really what is related to loudness. So again, pitch, loudness, what they look like. And the other thing to keep in mind is that sound is going to travel faster in warmer materials. So higher temperatures, warmer materials. It's going to travel slower in colder materials also. So slower in colder materials. And sound's going to travel faster in stiffer materials. So it's going to travel faster through water than air. It's going to travel faster than in like a solid than a liquid. So again, sound is going to travel faster if something's warmer, if the material that's moving through is stiffer. So that's going to affect how fast sound moves. It's going to be, around the same amount. It's going to be around 340 meters a second, but it might vary a little bit depending on these conditions. So the last thing is going to be an effect with sound that's pretty common to look at. So if you have a car and you're standing near it, or this car could be anything that's emitting sound. If that object, let's say the car is moving this way to the right, if it's moving away from you, that's going to sound lower pitched. So again, if the car or whatever that's making sound is moving away from you, it's going to be lower pitched, like this. So the pitch is going to be down if something's moving away from you. And then if something's moving towards you, so moving away, lower pitched. And if something's moving towards you, that thing's going to sound higher pitched. So again, if the car's moving towards you, it's actually going to sound, the pitch you're going to hear it's like it goes up. That's kind of a strange observation, but that's what happens with sound emitting objects, is that you're going to hear this kind of weird pitch shift. And this phenomenon is called the Doppler effect. So let me show you a quick clip of that. It comes from this link right here. And you're going to see, before I play it, you're going to see basically a car that has its horn on, and you're going to hear the pitch. It's going to sound higher, and then when it's going towards you, and then when it passes the camera, it's going to sound lower. So let's play that. So again, just a kind of a quick example of the Doppler effect. So again, that's really it for sound. So it's properties, how its speed can be affected, and then this Doppler effect. So last thing we're going to do a problem with this, with both of these, that brings in both of these sections. So again, please attempt this first before looking at the solution. There's more of a conceptual problem. Okay, so what we have here, the problem's asking, we have two sound waves, they're constructively interfering with each other. For the combined wave, is the following going to increase, decrease, or remain the same? So for the new wave that's produced from the interference, is it going to be, what's going to happen to these things, basically? So again, what would happen is if you had waves like this that line up, right? the crest and the peaks line up with each other. If you have two waves and they constructively interfere with each other, what you're going to get is, right, constructive interference. You're going to get a new wave that's going to look the same as the other two, except it's going to be larger, basically. I'm exaggerating the scale a little bit, but that's the idea. You're going to get a new higher amplitude wave. So, again, is the amplitude going to change if something constructively interferes? Yes, so you're going to have an increase in amplitude. B, is the frequency going to change? The frequency is actually not going to change. So again, the constructive interference is only affecting the amplitude. So again, it's going to still have the same pitch. So the frequency is going to stay the same. So frequency would be the same. So frequency is not going to change. The new wave will have the same frequency as either of the original waves. C, is the loudness going to increase, decrease, or remain the same? The loudness is going to increase because the loudness is proportional to the amplitude. So again, the amplitude goes up, the loudness is going to increase. This new sound is going to be louder. Is the pitch going to be affected? No, the pitch is going to stay the same because the frequency was not affected. So again, the pitch is going to be the same. The last thing, what's going to happen to the wave speed? Well, the wave speed, how fast the wave was moving, again, the constructive interference only affects the amplitude, so that really doesn't determine the wave speed. The new wave is going to be moving, same speed as the original two waves that came in contact in the first place. So the wave speed is going to stay the same. So again, that's the problem. Again, the thing to remember is that it's really only the wave speed that's being, or it's really not the wave speed, it's really only the amplitude and loudness that's going to be affected by constructive or destructive interference. Okay, that's the problem. Make sure you have everything copied down, and that's it for now.